we left off last class. We were talking about periodic trends. We also did some other stuff with like valence electrons and reading electron configurations based on our periodic table. But we left off thinking about atomic size. How big are the atoms? And we discussed that for atomic size, the size from the nucleus to outer electrons, the size increases as you go right to left. We talked about it as decreasing from left to right, but you just flip them and it makes sense. And that's because when we're in one of these rows, we've got the same access to like the biggest n number, n equals 1, 2, 3, 4, 5, based on the row. So that determines like how big our possible electron shell is, where we can fit all of our electrons in. And as we move left to right across the periodic table, we're adding protons, we're adding more positive charge. Because our electrons are negatively charged, they're going to suck in just a tiny little bit based on that increased positive charge in the nucleus. So that's why size decreases as we move left to right. It's not intuitive. We would initially expect that it increases left to right because they're getting bigger, they're getting more massive. But that's not the way that it works, unfortunately. And then the trend that does make sense, probably for most of us, hopefully, is that it increases as we move top to bottom. And this is because we're adding on layers to our shell. If we think of the Bohr model, where we've got our nucleus in the center and we've got our rings around it, basically every row that we're moving down on the periodic table, we're adding another ring. So it makes sense that it would be getting bigger. Okay, so thinking about those two trends, we want to choose the larger atom in each of these pairs. I've drawn them out the way that they are relative to each other on the periodic table. So think about what's the trend. So for lead or polonium, Pb is over here, Po is over here. Which one is going to be larger? Pb, lead, is going to be larger. It's further to the left, so it's larger. It has less protons, less positive charge in its nucleus, and so the electrons aren't getting sucked in quite as much. And they're in the same row, so that's the only comparison that we can make. And then for Rb or Na, we've got Na up here, we've got Rb down here. Which one is larger? Rb is larger. They have the meets after all. So Rb is larger because we've got extra shells added on. Think of like if we were comparing cakes, it was like Bake Off or something, and somebody did a cake that had 2 tiers and somebody did a cake that had 4 tiers. Which cake is taller? The cake with 4 tiers probably, unless they're really short tiers. All right, now we've got 2 trends going on at once. Tin or bismuth, which one is larger? So think about left, right, which one's larger? Think about top down, which one is larger? So we've got, if we're thinking about left, right, tin is larger. And then we'll call it up, down. Bismuth is larger. So just isolating the 2 directions that we can think about. So they're offsetting, they're competing. Probably bismuth is larger because of adding in a whole extra shell versus just the tiny little bit of shrinkage from increasing the number of protons. Bismuth is probably larger. When I give questions like this on exams, if I give questions like this on exams, I wouldn't give you one that has competing trends like we see in tin or bismuth comparison. All right, and then fluorine or selenium, which one is going to be larger? Selenium is going to be larger. Se is larger. It's further to the left, and it's further down. And those are the directions that atomic size increases. So since selenium's larger for both trends, it's larger overall. Questions about atomic size? Okay, more trends. Ionization energy. Ionization energy is defined as the energy, surprise, surprise, that's required to remove an electron, to take off an electron from an atom, and the gaseous state part is not really that important. You can think of it mostly as the energy required to remove an electron, to make an ion, but specifically by removing an electron. So energy to remove an electron. The gaseous state part is important technically, but for our understanding, not really that important for remembering the trend. So for example, sodium metal, if you take a block of sodium or an atom of sodium and you zap it with a beam of energy, which we can do, this is done all the time. You zap it with a beam of energy. If you hit it with enough energy, poof, one of the electrons pops off, and then you get sodium ions, and that electron just kind of floating around until it hits something. So ionization energy has the opposite trends of atomic size. It increases as you move to the right across a period. So two examples that we're going to think about, because it's a trend. So if we think about the extremes, if we think about the far left, if we think about the far right, the trend in between should hold as well. So removing an electron from a group 1A element, an alkali metal, gives it noble gas configuration, and that is what it wants. And so that's going to be the easiest case. The other way that we could remember this is metals, things that are on the left side of the periodic table, tend to lose electrons when they undergo chemical reactions. They want to lose electrons. They preferentially form positive charged ions. So things over here on the left, the way that they are typically going to react is removing an electron, giving an electron away. If we go to the other side of the periodic table, a group 7A element, a halogen, like fluorine or chlorine or bromine, moves away. If we take an electron, it moves away from noble gas configuration. And to the element, this is very bad. This is the wrong direction. So looking at our halogens, right, they want to gain an electron. We are doing the opposite here. We are taking an electron away, and they get very upset at that. They do not like it. We can also get ionization energy for our noble gases as well. Noble gases also hate this. Ionization energy decreases as we move down a column. As we're moving down our periodic table, it decreases. And that's related to the atomic size. So we're adding on different layers, right? So the further down we get, the bigger we get. So plucking off one of these electrons, if it's way far away from the nucleus, it's going to be a lot easier than if it's right next to the nucleus. If you think about two magnets, if you've got two magnets and you're holding them at arm's length apart or a distance apart, and you try to pull them apart from each other, they're probably not interacting at all. If they're touching each other, if they're right next to each other, probably a lot harder to pull apart. I should have brought my dangerously strong magnets for this demo. I've hurt myself with these magnets. They're for a physics demo. Anyway, okay, all that aside. So as we're moving down a column, ionization energy decreases. Because the electrons are farther away. So ionization energy and atomic size are inversely related. So the trends are the opposite, which is convenient because then if you just remember one of them, like you've got it locked down, and then you remember the other one is the opposite, congratulations, you've gotten two basically for the price of one. Any questions about ionization energy? Again, it's to remove an electron. Zap an electron off. Okay, so ionization energy increases up and to the right. If you had to take a guess, what element is going to have the highest ionization energy? It's not fluorine. Helium. Helium has the highest ionization energy. It's really small. So those electrons that we would be stealing are right next to, or as close as we can possibly get to the nucleus relative to our other elements. And it's already got its full outer shell. That's why it's in the noble gas column or group. So it's got noble gas configuration, and taking that away is going to be tragic for it. It will not cope. And typically, if you make helium an ion, it immediately undoes it. Like the soonest possible opportunity, it runs into something and it says, I'm going to steal your electron, I don't care what you are. Which is very cool. Okay, ionization energies. We want to compare ionization energies for some pairs. Maybe a Bosch pair, Asian pair, who knows? Okay, so we've got Mg or Sr. Which one is going to have higher ionization energy, harder to remove an electron? Mg. And I'm going to abbreviate ionization energy, IE. In this case, we can think of it because it's smaller. It's got less shells on it, so the electrons are closer. It's harder to remove them. All right, In or Te. In. Te, which one is going to be higher ionization energy? Te has higher ionization energy. And the reason that it has higher ionization energy is it's further to the right on the periodic table, so it's pretty close. It needs 2 electrons. It needs to gain 2 electrons, and then it's got noble gas configuration. It would love to pick up 2 electrons. It really would not like to move the opposite direction. So if it loses an electron, it's getting further away from its dream, its goal, its mission, its purpose in ionization. Indium, on the other hand, is actually not too far away. It might form a 3+ ion, because we kind of just ignore the transition metals, as we usually do. So it's closer to the noble gas column in terms of left-right. All right, and then we've got carbon and phosphorus. Carbon, phosphorus. Which one has the higher ionization energy? If we're thinking left-right, which one's higher ionization energy? Phosphorus. If we're thinking up-down, it's the carbon. I don't know. It's a guess. Your guess is as good as mine. So who knows? I would guess that it's maybe the carbon just because it's smaller. I could look them up because you can just like look this stuff up, but then it just wouldn't be as fun to also not have an idea of which one is higher with you. So that's why I don't. allegedly. Okay, fluorine, sulfur. Which one's higher ionization energy? Fluorine. Fluorine is higher both ways. Questions about ionization energy? Okay, another periodic trend, metallic character. Where do our metals live on the periodic table? Left or right? Left. And if we had to, like, let's say we're looking at our P block, where do our metals live, up or down? Looking at our P block. We've got our metalloids kind of in this middle, along that diagonal. Which way is Metal Town? Is it north or south? South to Metal Town. So, congratulations, metallic character, you've got it. It's increasing to the left because that's where our metals live. If we're looking at the right side of the periodic table, I almost dabbed on you, sorry about that. If we're looking at the right side of the periodic table, our P block, right, nitrogen, oxygen, fluorine, are nonmetals. If we go down to bismuth, polonium, astatine, those are kind of more in the metal-y territory. And so metallic character also increases as we move down. So metals tend to lose electrons in their chemical reactions. Nonmetals tend to gain electrons. And so metallic character is associated with losing electrons. Voted most likely to lose electrons. So this is sort of the opposite of ionization energy. Ionization energy is how hard is it to remove an electron, and metallic character is more like how much does it want to lose an electron. So they're opposites in that way. And this follows the same trend as atomic size. And look at that. Metals on the left and metals further down. Metals are L and D, left and down. Okay, let's choose the more metallic element from these pairs. We've got Sn and Te. SN-Te, which one is more metallic? Sn is more metallic. Tin is more metallic. Because it's further left. And then what about Si or Sn? This one is also tin. It's more metallic because it's further down. It's easier to pluck an electron off. Tin is also a metal. Silicon is a metalloid or semi-metal. So that would also work. And then we've got Br or Te. Br and Te. What do we think? Te is more metallic. It wins on both trends. Further down low. All right, and then we've got Se or I. What do we think? Selenium or iodine? It's another shrugger. I don't know. Again, I won't give you ones that have conflicting trends in this class. Any questions about our trends? Okay, so our trends, just to recap before we get into representing valence electrons with dots. We've got atomic size and metallic character. These both increase to the left and down. On the other hand, we've got ionization energy. Which is the opposite, it increases up and to the right. Those are our three periodic table trends. So if you wanted to remember the names and the direction of like ionization energy and the other two are the opposite, that would work, probably. Would be a good idea to have a basic understanding of like why and what we're talking about, like how are we measuring atomic size, how are we measuring ionization energy, like what are we looking at specifically. It's nucleus to the outer electrons for atomic size. For ionization energy, how difficult is it to remove an electron? All right, representing valence electrons with dots. So big part of the reason we learned about valence electrons is because valence electrons, because they're the outermost electrons, they're the ones that can react. And so we are going to learn a bonding theory, a theory for how atoms bond together to form molecules. So we know that atoms, individual pieces of elements, can interact with other individual pieces of other elements or the same element, and they can form molecules. And so bonding theories can help us predict what combinations work, what combinations form compounds, what combinations do not form compounds. We can predict the formulas of compounds beyond what we've done with ionic compounds, because ionic compounds we can do the charge, the swap and drop, the crisscross. We can do that to predict the formulas. We don't have tools to do that for molecules since molecules are nonmetals only, they're not charged when they're forming molecules. So we don't currently have tools to predict what those formulas are. Bonding theories let us do some of that. They'll also let us in the shape of molecules, predict the shape of molecules, and the shape of molecules is important because it determines their physical and chemical properties. So for example, the reason that oil and water don't mix together is related to bonding theories. The theory that we are going to learn is Lewis theory, because it's simple and it's quick, relatively speaking. You don't need a supercomputer to do Lewis theory, basically the takeaway there. Okay, so in Lewis theory, the valence electrons, the outermost electrons of main group elements, so we're ignoring our transition metal block, right? We're just looking at our main group elements, where the column number with the A designation, or if you drop the 1 in front, that's the number of valence electrons. Those are represented as dots. So a dot equals an electron, and we put them around the symbol of the element. The result is a Lewis structure or a dot structure, or sometimes called a Lewis dot structure. And it's equal to the group number with the little A designation. Sometimes you'll see it in whatever the numbers that we use are called. I can't remember the name. Sometimes you'll see it in Roman numerals. Helium's an exception to that because helium only has 2 electrons. So the electron configuration of oxygen. We need to find oxygen on our periodic table. We find oxygen. It's got 8 electrons. We are past row 1. In row 1, we have access to only the S subshell. And we're past it, so it's full. S fills up with 2. We're in row 2 now, after helium. Lithium, beryllium, we are past those. That's row 2, and it's the S block. Since we're past it, we're past both of our columns in our S block. 2 columns in our S block. We're past both of them, so we've got 2s2, row 2, S block, 2 of them. And oxygen's in the 4th spot, row 2 in the P block, so it's 2p4. P block, so this right side, it's the 1, 2, 3, 4th spot, row 2, so it's 2 in the P block, P, 4th entry, 2p4. How many valence electrons does oxygen have? 6. So our electron configuration confirms that we have 6 valence electrons. 6 valence electrons because our row 2 is our highest shell number, principal quantum number, and we've got 2 plus 4, which is 6 electrons. We could have also gotten it just from the column that it's in on the periodic table. That's usually how we'll do it, but just to remind ourselves of where it comes from initially. Okay, so the Lewis structure for oxygen, we've got oxygen symbol in the middle, and we have to put 6 electrons around our symbol for oxygen. We put them in the 4 cardinal directions, north, south, east, west, and then we can pair them up after we've gotten 1 dot in each of our 4 directions. So it might look something like this. 1 dot equals 1 electron. Okay, so each dot represents a valence electron. So we write that symbol in. Each of our dots represents a valence electron. We place them around the element symbol with a maximum of 2 per side. The location is not really that important. I'll usually fill them in a particular way, but that's just habit more than anything, or I know what's coming next, so I'm preparing the way. We fill in the dots singly first and then pair them up later. So for example, this is the one that we drew. You could have also drawn it like that, like this, like this, and there's probably some other combinations that I don't feel like drawing. Those are all equally valid. Atoms with 8 valence electrons. What on our periodic table has 8 valence electrons? What column or group is going to have 8 valence electrons? Noble gases. Noble gases are especially stable. That's why you can breathe them in without dying, at least right away. Don't only breathe them in. You should also breathe air. So 8 valence electrons, like noble gases. For example, that's a free example for you, are particularly stable. Very good. We want to be stable. We want to be happy. Stable you can also think of as happy. 8 dots we call an octet. oct like octopus. Or if you had 8 people singing all together, that would also be an octet. Like a quartet's 4 people. Anyway. So our goal generally for Lewis structures is full octets. Octet's the goal. Let's write out some Lewis structures for our first 10 elements. I'll get us started with hydrogen, 1 dot. How many dots are we going to have for helium? 2. Great. So I'll give you some time to work on doing the rest of those just so we've got some practice. And please compare with your neighbor if you have one. Okay, how are we feeling? A little crazy? Absolutely dotty? Okay, so hydrogen, we've got 1, because we have 1 valence electron. We said that for helium, we've got 2. And helium, I would put the dots together because we've got a full 1s shell. It's probably not that important. Now here's where some of you may have gotten tripped up. What column, what group is lithium in? What's the number? 1. It's in column or group 1. 1. So it's got how many valence electrons? Also 1. So our count restarts. So for lithium, we've got 1. Beryllium's next up. It's got 2. Boron then has 3. Carbon has 4. Nitrogen has 5 with 1 pair. Oxygen we saw has 6. Fluorine is 7. And neon left no crumbs. 8. Note that helium is stable with a duet of just 2 electrons. Questions about our Lewis structures? Usually you're not going to be doing a series, so you won't fall into this trap, hopefully. So those are our Lewis structures. In Lewis theory, our bonding theory, a chemical bond involves sharing or transfer of electrons to get stable electron configurations. Any idea what a stable electron configuration might be? What's a stable number of electrons to have? An octet. So our goal is 8 electrons for each of our elements, with exceptions of like helium and lithium and some other small things, and hydrogen. So we've got ionic bonds that involve a transfer of electrons, like in ionic compounds, when we've got metals reacting with nonmetals. And in covalent bonds, co like sharing, like cooperative, covalent counts for both valences, the electrons are shared. So like in molecular compounds. And that's the new and fun and exciting part of Lewis theory, is that we can do covalent bonds. So our octet rule, this is our big guiding principle for Lewis theory. Atoms transfer or share electrons to obtain outer shells, valence shells with 8 electrons. So we want 8 electrons on the outside. You can also get rid of all the electrons as long as there's a shell underneath, because then secretly, there's an 8 underneath. Some of our small stuff, hydrogen, lithium, beryllium, hydrogen's most important here, follow the duet rule. Hydrogen is happy with 2 electrons. Hydrogen will only ever, when it's bonded, have 2 electrons. It will never have 3. It's never going to go to 8. It's only 2. All right, let's look at an example of ionic bonds. We've got structures for aluminum and selenium. And I think we're just doing the Lewis structures for aluminum and selenium here. We'll do some bonding later because it takes a lot of time. Okay, so aluminum, Al. Al on our periodic table. Group 3A, 13. It has 3 valence electrons. Selenium, 6A, 16. 6 valence electrons. When these form a compound, when aluminum and selenium react, aluminum, the metal, gives electrons to selenium. How many electrons is our aluminum going to give to selenium? What we're thinking about, how many electrons does selenium need? How many electrons does Se need to get its full octet? Needs 2 electrons, so it's going to take or receive 2 electrons. Aluminum will still have 1 electron left, and so we would have to give that away to another selenium. We'll look at more of the bonding stuff in a bit. This is not the complete story. This is just the first step. Okay, so when metals bond with nonmetals, electrons are transferred. Moved, stolen, given, taken, however you want to think about it, as long as they're going from one to the other. The metal loses electrons, it becomes a cation. The nonmetal becomes an anion. And they become the cation and the anion that we expect them to be. They live up to expectation. So things that are in our alkali metals form 1+ ions. Our alkaline earth metals, column 2, group 2, 2+ charge. Group 3, A, 13, 3+ charge. And then our nonmetals, our halogens, 7A, 17, 1-. Our chalcogens, 16, 6A, 2-. Next to them, the nitrogen group, nitrogens, 3-. And that attraction between the positively charged cation and the negatively charged anion result in an ionic compound. We represent this by moving the electron dots. So if we have a reaction between potassium and chlorine, potassium is K. It's got 1 valence electron. It's an alkali metal. Chlorine, Cl, is a halogen. It's got 7 valence electrons. So those would be our valence electrons shown as Lewis dot structures. And the bond, the electron transfer, is the electron moving from potassium to chlorine. So this turns into K with a positive charge. Chlorine has gained an electron, and it has a negative charge. And the way that we show that it has a negative charge is we box it in with brackets, and then we put the charge outside of the brackets. The brackets are important because it says everything that's inside the brackets is together. So what we're doing here is we're saying this whole thing together has an overall 1- charge, and these dots that are between these two only belong to chlorine. These are just chlorine's dots. Nobody's sharing dots with chlorine. So chloride ion has an octet. It's got its 8 valence electrons. Potassium lost its only valence electron. So if we look at potassium on our periodic table, if we lose one electron, that's like moving one spot over to the left on the periodic table, which means that we would move back to argon. And so it has the electron configuration of argon, and that makes it have a noble gas configuration. So it is also happy. It secretly has an octet. So it also has 8 valence electrons. So taking off the shell or adding electrons to complete the shell, those are both valid methods of getting an octet. And again, the Lewis structure of the anion, which was the chlorine, gets written with brackets around it and the charge in the upper right corner outside the brackets. This is for any ion, not just if it's a monoatomic like chloride. Do we have any questions so far? Okay. Please write the Lewis structure of the compound neighbor, sodium bromide. Okay, our Lewis structure for our compound, NaBr, we've got sodium. Sodium, Na, has 1 valence electrons. It's in the first group, the first column, the 1A, the 1. So it's got 1 valence electron. And then we've got bromine. Way over on the right side, it's in group 17, column 17, 7A. So it's got 7 valence electrons. So we draw in 7 dots, maximum of 2 per side with 4 sides. And then the compound that forms, sodium, because it's a metal, transfers its 1 electron over to the bromine to become bromide. So we've got sodium plus brackets to contain our negatively charged bromine. Just going to quickly draw in the dots. Other bracket, and a negative charge outside of the bromine. Questions at all? As I believe I've previously mentioned, we're not stopping at Lewis structures. We're using Lewis structures to build up to do another thing, and then we're going to do another thing on top of that. So it's important that we understand Lewis structures. If you're lost or confused, my office hours, Logan's SI sessions, great opportunities for you to get some extra help. You could also ask questions during lab. Okay. We can also do this with things that are not just 1 plus and 1 minus charges. So for example, with calcium chloride, we can predict the structure of calcium chloride using our Lewis structure. This is not typically how we would arrive at a formula for ionic compounds because just swapping and dropping the charges is just way faster. But to show you that it works, we're doing some Lewis structures for it. That was me slapping on the tape on the big tank of water that's leaking, in case you were wondering. Okay, so we've got calcium. What group, what column is calcium in? Ca? 2. So it has how many valence electrons? 2. So it gets how many dots? 2. 2 dots. Separate sides. Chlorine. Cl has how many valence electrons? 7. How many electrons does chlorine need to be happy? One. Just one electron, Mom, and then I'll be happy. So let's transfer that electron. Boom. I'm actually not going to leave it like that because it's confusing if you look at it later. Okay. Chlorine's happy. Love that for chlorine. Is calcium happy? Calcium is not happy. Why is calcium not happy? It still has one electron. Where could it get rid of that one electron? Another chlorine. There's another chlorine. A second chlorine has entered the picture. Me whispering into President Bush's ear. Okay. I'm sorry, I'm well rested. That's my bad. Okay, so we transfer that to another chlorine. Other chlorine, is it happy? Yes. First chlorine, is it still happy? Yes. Calcium, is it happy? Yes. We did it. Okay, so chlorine, calcium, other chlorine. Just like that. What are we missing? Charges. We're missing charges. Calcium's a 2+. Our chlorides are 1-. Is there anything else we're missing? Brackets. Which when you do it, kind of looks like you're eating a really big cheeseburger. And that would be our final Lewis structure. This predicts the formula CaCl2, which we would have also gotten if we just swap and drop, crisscross the charges. So again, not the way that we're typically going to do it. We still need to know how to do it. Most of you'd probably get lost with brackets. Brackets is probably where most of you are going to, that's the one thing that you're most likely to forget, I would say. Do we want to see a more complicated one? A very confident yes from the audience. Thank you. Okay, so we've got Lewis theory to predict the formula of the compound that forms between magnesium and nitrogen. What is the symbol for magnesium? Mg. What is the symbol for nitrogen? N. How many valence electrons does magnesium have? 2. How many valence electrons does nitrogen have? 5. Who is losing electrons here when they transfer? Magnesium's losing electrons. It's donating electrons to nitrogen. It's got 2 electrons to give. Okay, so magnesium gave away its 2 electrons. Is magnesium happy? Yes. Yes, magnesium is happy. Is nitrogen happy? Not quite. What does it need? 1 more electron. Where could it get another electron from? Another magnesium. So another magnesium is going to have 2 valence electrons. It can give away one of those electrons to nitrogen. Is magnesium, number 2, happy? No. It's not. Is nitrogen happy? Yeah. Yes, nitrogen is happy. So nitrogen at least is good. For magnesium to be happy, what needs to happen? Needs to give away this other electron. Where could it give away that other electron? Another nitrogen. So we're going to draw in another nitrogen. So there's another nitrogen, also with 5 valence electrons. So our magnesium can give away that one electron to the nitrogen. Is magnesium number 2 happy? Yes, it has that full octet. We stripped off the outer shell. Is nitrogen happy? No, it's not. What does it need? It needs 2 more electrons, so we need another magnesium. So another magnesium enters the picture, and it gives away both of its electrons. And now, is our nitrogen happy? Our second one, yes. Is our third magnesium happy? Yes. Okay, so we've completed the cycle. This would have the chemical formula Mg3N2, which again, we could have gotten so much faster if we just swap and drop charges. But it's the same thing that we got if we swap and dropped the charges. So just a little bit more evidence that the method works. And I'm not going to draw it out with all the brackets and the charges and all that. Okay, so that's ionic compounds. Ionic compounds where we're just transferring the electrons. So our new tech is covalent Lewis structures. Covalent, the co part meaning shared, and the valent, like valence outside, referring to our electrons. So these are shared electron Lewis structures. When nonmetals bond with other nonmetals again being stuff in this upper right corner of our periodic table, hydrogen also included in that most of the time. When those things bond, a molecular compound results. So molecular, only nonmetals, no metals in my molecular compounds. And these electrons are shared, so this is different from with the transfer. Covalent bonding is represented by neighboring atoms sharing some of their valence electrons, again with the goal of octets. So this is still the goal. We are still going for 8 valence electrons. It's just a little bit of a different mission because we're sharing. Okay, so Lewis structures for hydrogen and oxygen. Hydrogen has how many electrons? 1 dot. Oxygen has how many electrons? Valence electrons. 6, so 6 dots. In water, which is H2O, we share electrons between our hydrogen and our oxygen. So this is one way that we can draw it out. I've just drawn them connected. Typically, we would see this if we're using dots. We'll do hydrogen's electrons in red. One way that we can do Lewis dot structures is like this. So we've got a pair of dots between hydrogen and oxygen. Those count towards both octets. So dots between atoms count for both counts. So our hydrogen has how many valence electrons in our structure? How many dots is it touching? It's touching 2 dots. Hydrogen's happy with 2. That's one of our exceptions to our octet rule. It's a duet. So the hydrogens are happy. How many dots are around our oxygen? 8 dots. That's a full octet. So oxygen is also happy. So in our water molecule, the hydrogen and the oxygen are sharing their electrons. So the hydrogen gets its duet, gets its 2 electrons that it wants. The oxygen gets its octet, its 8 electrons that it also wants. Those shared electrons count towards the octet or duet of both atoms. So this is another reason why we drew the brackets when we were doing ionic compounds. The brackets let us know they're not shared electrons, because if we don't have the brackets, then it looks like shared electrons. So that's another reason that we have to do the brackets in our ionic compounds. We've got 2 different types of pairs. We've got bonding pairs. Bonding pairs are shared between 2 atoms. We also have lone pairs or non-bonding pairs that are only on 1 atom. So let's look at H2O again. So in H2O, we've got bonding pairs that I'll circle here in blue. Those are shared between 2 atoms. It counts for both octets or duets. That's the way that sharing works in the Lewis model. Our lone pairs count for only one of the atoms. So these are not shared. So this is one way that you can represent Lewis structures or in Lewis theory. The other way that I like better is with lines. So I will typically be doing the line version. I'll draw the lines in blue. So this is an equivalent Lewis structure to the one that we saw up above. We've converted our dots into lines. Each line is a bond. And is 2 electrons. So when we're looking at our octets or our duets, we count each of these lines as 2. So we've got, for oxygen, we've got 2, 4, because of the 2 bonds, 6, 8, counting our non-bonding or lone pairs. So we still have our octet for oxygen. Hydrogen has 1 bond, so it has a duet. Hydrogen will only ever have 1 bond, because it only needs a duet. Hydrogen only forms 1 bond ever in this class. Questions about our new stuff? Okay. Lewis theory also explains why our halogens form diatomic molecules, our Brinkelhoff, our H7, our horse's knee oats for clear brown eyes. Those guys? It explains why the halogens in particular form diatomic molecules. So the fluorine, chlorine, bromine, iodine part of those mnemonic devices, they form diatomic molecules. So if we look at a Lewis structure for bromine, let's say that bromine is just floating around with its 7 valence electrons. Is it happy? It's not happy. What does it need? 1 more electron. Let's say that bromine's hanging out with its bromine. So we've got 2 bromines hanging out. Usually if you've got one, you're good chance you might have 2. They each need 1 electron. If they share, what happens? They did it. They got their full octets. So by sharing, by forming a bond, a covalent bond, they get full octets. So they're sharing 1 electron, 1 bond. They're each contributing 1 electron into the bond. Gets them to their octets. So now they're stable, they're happy, they've got their octets. Mission accomplished. It also predicts that hydrogen exists as diatomic molecules. So thinking along the same lines, hydrogen has 1 valence electron, 1 electron. It can also form a bond. So hydrogen bonded to another hydrogen with the line. Again, the line is 2 electrons. The hydrogen on the left, since it has 1 bond, has 2 electrons. It's got its duet. The hydrogen on the right also has 1 bond, 2 electrons. So it's also got its duet. So the hydrogens are happy. So Lewis theory does a nice job of explaining that for us. It also explains some other things. So for example, when I talked about 1 line equals 2 electrons and each line is a bond, we can have multiple lines. So we don't just stop at 1 line all the time. We can have more lines. So let's look at oxygen. Oxygen has 6 valence electrons. If there's another oxygen around, it also has 6 valence electrons. So we'll mirror that. And oxygen needs how many electrons to get an octet? 2, right? It has 6, so it's 2 short. If it shares 2 electrons, so sharing 2 electrons from each oxygen, then we get the oxygens with their lone pairs, the 2 bonds, the other oxygen. And now if we do a count, each of these has 4 electrons from the lone pairs. The lone pairs are here in green. So these are electrons that are only on one of the atoms. So the left oxygen has 2 lone pairs. The right oxygen also has 2 lone pairs. We've got 4 electrons from lone pairs, LPs. We've also got 4 electrons from the bonds. We've got 2 lines. Each line is 2 electrons. 2 times 2, 4. So 4 electrons from 2 bonds, which we would also call a double bond because there's 2 of them. Any questions about what's going on there? Oxygen, also one of our diatomic molecules. Lewis theory helps us explain why that is. So we'll talk briefly about double bonds, and then we'll leave triple bonds for next class. So our double bond is when 2 electron pairs, a pair being 2 electrons, 2 electron pairs are shared between 2 atoms. You can only share between 2 atoms. Double bonds are shorter and stronger than single bonds. If you think of bonds as like rubber bands, the nuclei of our atoms are positively charged. They don't want to touch because they're positively charged. Opposites attract, and the opposite of that is that like charges repel. Right? So positive charges, they don't want to touch each other, but if they've got bonds between them, that'll bring them close to each other. If you add another bond, another rubber band, it'll pull them closer together. Right, so double bonds are shorter. They're also stronger than single bonds. The distance between oxygen nuclei in an oxygen-oxygen double bond is the very short 121 picometers. Compared to a single bond, which is just 148, which is longer, picometers. So we'll stop there and pick up next week.